now with a little bit better marker. So we were at acceleration as gm divided by the radius of the sun squared. And I'm being a little bit careless with units, but everything here is SI, kilogram, meters, and seconds. So it's going to work out. So this looks like one of the sevens goes away, so we're left with 2 over 7, which is 3. And now we've got 16 here, and 30 here, so that's 14. Minus 11 is 3, but we divided 2 by 7, so we gotta make it 2. Alright, so that's 300 meters per second squared. So that's not so bad. If you were on the sun, you would still be okay. Now, it's important to note that this is only a maximum acceleration. So this is when the light is just grazing the surface of the sun. But in this first approximation, what we're going to do is pretend that the sun doesn't impact the ray of light at all until it gets to the borderline of above the outer edge of the sun. And it stops interacting with it right about here. And in between those interactions, it always has a constant acceleration. So we want to figure out what happens to the angle of the velocity. The velocity in the x is going to be about speed of light. Whereas the velocity in the y is the stuff that's caused by this. So we want to figure out how much time this acceleration has to act. That time is just the diameter divided by the speed of light. Sometimes this thing called 2 times the radius, this period where gravity of the sun is pulling in the light, is called an impact parameter. It is sometimes written b. So this is the impact parameter. And in our case, the impact parameter is 2r. Now you might ask, okay, why did I pick 2r? There's no reason. I just picked 2r. Okay. So we've got this time, and in this time, we've got this acceleration acting. So as a result, I bet you guys can do this faster than I'm erasing the whiteboard. Go do it. Okay, so the final y velocity is going to be the acceleration times time. So so this is 2 times 7. that's 14 times 100. So that's 1400 meters per second. Okay, well, you might care to know what this angle of deflection does this correspond to? So there's a y component of the final velocity. If this is our coordinate system here, then the final velocity has an x component and a y component. So the tangent of this angle is Vy over Vx, but for small angles, tangent of the angle is about equal to the angle itself. So theta is about equal to 1400 divided by 3 times 10 to the 8th. So that's 10 to the 3rd. So we're going to get, and 14 over 3 is 5, and we're going to be left with 2 powers of 10 here after the 5 goes out, and then we've got this 10 to the 8 at the bottom. So we're going to get 5 times 10 to the minus 6. Okay, well, let's write that in some kind of astronomical terms. This is in radians. So if we want to get seconds of a degree, we're going to multiply by 180 over 2 pi, and then multiply by 3600. Again, you guys can beat me here. Okay, so pi is like 36. And 18 is like 2, 20. Okay, so we've got 5 times 10 to the minus 1. We've got half of a second of 1 degree. So during things like solar eclipses, this does get measured. The real life number is 1.8 or 1.7. So this is a little bit rounded, but it's not so bad. Okay, so let's talk about ways to improve this. Well, I did this calculation without assuming that the impact parameter is from here to there, and not assuming a constant acceleration. And that's going to change this 0.5 to 0.85. But it turns out that you'll still only get half of this value, and the discrepancy there starts lying in the post-Newtonian correction to gravity. So we'll talk a little bit about that on the homework problem, that if I was to assign one, maybe I'll assign one. All right, have a nice day.